Okay, so before we start, I wanted to give a few, I guess, logistics items. As you know, there's a final project at the end of the semester, and I have statements. So this is we have teams of two. I think we have we count for shots. We said he was interested in doing other than the class. I think we have 9 people. So he's not divided by 2, so I'm a team of 3. But just kind of going through the main elements here. The project is composed of basically a oral presentation and also a written report. And this constitutes a considerable amount of your grade, I think 40% of the grade. So as expected, this is to be done at a pretty high quality. In terms of other workload during the time period, there will still be journal presentations. About half of you are done right now, so some of you will have a presentation in the middle of that. We're gonna have one more homework assignment, 3 as opposed to 4, just because we're getting close to the final project time. I want the final project to be done. The quality not to be homework. But the main thing is composed of presentations, reports. Presentations will be held November 27th, 29th, and December 4th. And these are going to be around 30 minutes long with about 5 minutes for questions. It takes us 2 to 3 days to get through all those. Let's see what else. There are 2 basic tracks. Track 1 is description of the physics of existing process. Okay, so we've gone through the AM physics of some AM processes, and we haven't gone through all the physics of even those AM processes. Right? They're pretty complex. So you are tasked with describing something that we have not directly gone over in class. If you want to do metal powder bed fusion, there's something that we have not covered that you really want to describe. That's fair game. You're just going to go through all my notes on lasers impinging on the surface of powder bed fusion, top surface of powder bed fusion system. That's probably not going to get you a good grade, but that by all means does not rule out having that as an aspect of the physics. Right? That's what drives temperature gradient, which then drives other aspects. Right? So, I'm not here to discourage you from using some of the things in class. You should hopefully leverage it in class. You can't just recreate something in the class. So basically, pick an AM process as existing and propose some part of the physics and propose an experiment then to test that physics. Right? When you get down to the actually a longer description, when you say experiment, basically you assume that you have unlimited resources. So if you say I want a neutron diffraction instrument, just assume that you have it in your basement house. So unlimited resources in terms of what the track 2 is devise a new AM process and perform a complete complete analysis of assumed physics and resulting properties. I'm not sure exactly where this will go. This one's a little bit more open-ended, but I figured I'd have it out there in case you wanted to really think outside the box and see if you can think of new ways to basically add materials to each other to then create something new. And maybe it's new and useful, and maybe it's just another AM tool of the many that doesn't get used that much, right? But it's just kind of used to kind of open your mind and think about how you could potentially add material. What could be the potential benefits of this AM process over not to say you're going to displace some existing process, but maybe there's something unique that has a niche market. Right? The other thing I wanted to mention too is that students are encouraged to choose a final project that will complement their graduate school research. For those of you who are doing research projects, if there's something that complements the work you do, that's definitely encouraged. Classes in graduate school are primarily to make you better at what you're doing in research wise. So I think this class should be the same as well. You can't just take a conference paper you've written and turn it in, of course, but something that can complement that. And really the ideal situation is a really good job on the project, the simulation, they really describe something, and you turn this into a small journal or a small conference paper. Ideal situation. Then the evaluation rubric is given at the bottom. How you'll be graded on this. Any questions on the final project? Okay. So I'm gonna just leverage. We have an existing Google sheet that kind of tabulates who's giving what presentation for journal articles right now. I'm just gonna add another tab to that, and you can sign up for. I'll put all your names on there too, so if you have trouble contacting each other, you can contact each other. Names and emails, you can contact each other and say, hey, I want to be your partner on this project, etc. That hopefully try and organize the groups, and also when the groups will be presenting to assign dates for the presentations. Any questions? Okay. All right. Thank you for participating. For those of you who are here on, I guess, a week ago today, we had a kind of informal review of how the class is going. I just wanted to go through that and thank you for your comments. I think they were helpful. There were, I'd say, 3 consistent themes throughout. One is a request for more timely responsive post-name annotated module solutions and grading of homework. I agree. I think this was just maybe the kick in the butt that'll help this situation out. So I'll do a better job of that. Lack of details in the solutions. So from here on out, I'm going to try and make the solutions a little bit more detailed, go through them a little more carefully. And the other consistent theme, I wasn't sure how this was going to go. I added this component maybe like a week before class started or so, because I thought maybe it could be a good aspect of the class. I didn't know how it would go, but in general, students seem to like the journal presentations and find them useful. So that was good to hear. I wasn't sure how this was going to go in the class. Suggestions. I thought there was one suggestion that I think could be beneficial to the class. So one student asked to see AM machines on campus. So I'm going to organize some sort of tour. So I tried to do this very early on with welding, and then after like 3 emails without them responding to me, I dropped it. So I have restarted this with CDME actually, and we'll see if they're a little bit more responsive, not responsible. So I agree. I think this would be helpful. CDME has a lot of tools. I'll see what the response is. I sent an email to them this morning to see if we could have a tour, but I think that could be helpful. They have quite a few tools running. The reason why I didn't contact CDME originally is because they have some ITAR restrictions. ITAR is I don't know exactly what the acronym stands for, but yeah, exactly. So I'm not sure that we'll see what they say, but there is a chance that not all students would be able to see everything in CDME. Yeah, so that's why I didn't go to them originally, but we'll see what they say. And maybe there's a situation where, so I know they do have some defense contracts, and there may be situations when they're not running defense-related projects at that point in time. Everyone can go see it. So, okay. Yeah. Okay. They might have PM. I don't know where they have. Okay. That could be an option. Okay. All right. Thanks. All right. Any other comments, suggestions, things that you may have written down that you think are reflected in these summary? Okay. All right. All right. So thanks for your comments. That's helpful. Okay, so since it's been a week since we've met last, I wanted to quickly get us back up to speed here. Okay, this is just a little bit prior to where we left off on Tuesday. So we were looking at material extrusion processes, so we're trying to understand material extrusion processes And we got a little bit past this, but we first are starting with the basic architecture. So we have melt processed material extrusion processes. In both cases, the architecture looks fairly similar. And so we're going to describe the fairly similar manner as well. So in both cases, you have some sort of reservoir. This is where material, liquid form material is stored. In this case, it's heated. It's liquefier. And in all cases, you have a nozzle, which is you have some sort of converging of this channel to a smaller diameter. And the material is then extruded through this small diameter. And then room temperature processes, similar idea. You have a reservoir, convergence into a nozzle, and then extrusion of the nozzle. We're trying to describe fluid flow through this system. And we started off by just looking at what does fluid flow look like through circular channels. One thing to note is that to describe fluid flow through circular channels, it makes sense. So pretty much so far in this class, I'll do Cartesian coordinates. So in cylindrical coordinates, we have the z direction, in this direction, radial direction in this direction. And it's not shown very clearly here, but you also have theta direction in cylindrical coordinates. So if we have fluid flowing through a circular channel, this would be the walls of this channel. And we can look at just a unit element of fluid, right, or a plug of fluid flowing. And we can say this plug has a pressure difference across it. So in this edge of the plug, we have pressure of P, and this we have P plus delta P. So since the shear stress is given in the negative z direction, now we know that delta P must be less than 0. The pressure on this side of the plug is greater than the pressure on this. So fluid flowing in this channel is going to have pressure on one side and also shear stress resisting flow, because we'll get to the flow profiles in a second, but basically in the center, the fluid is moving faster than at the wall. Okay, so since we have basically sheets of material moving past each other, there's going to be shear stress as these two different materials are passing each other. So the molecules on this side of the wall, this side of the wall, given friction or basically viscosity between this is going to cause a shear stress. So then the first example we're going to do this is we're going to derive the well-known Hagen-Poiseuille equation for well-developed laminar and steady-state flow of a Newtonian fluid through a channel with a given with a circular cross-section. So this statement actually gives you this relationship already, and we're going to try and find this. So for those of you who have ever taken a fluid mechanics class, you've probably seen this before. Anyone who's ever worked with microfluidics, probably seen this. This is used a lot in also AM. So very well known relationship between pressure drop, and flow rate in circular channels when you have laminar. So the basis for this is continuity equations and also the Navier-Stokes equation. When we wrote this originally in the fluid mechanics section, we started with Cartesian coordinates, and it's going to be not as convenient to work with Cartesian coordinates. So instead of working with your velocity vector, velocity x, y, z direction, we're going to work with the velocity vector. Is going to be in terms of velocity in the r direction, velocity in the theta direction, velocity in the z direction. So once again, just to augment this plot, this would be theta direction.
So before we get into kind of the details of this, I just want to point out is that velocity in the radial direction would be, this would be r. And since this is laminar flow, the laminar flow is that a molecule that starts here, upstream, remains here in terms of the radial direction. Right? So the flow flows in sheets, right? As the flow lines don't cross each other with respect to the center of this cylindrical channel. Right? So we are going to expect in all our analysis that U r is equal to 0. U theta would be basically molecules going around the circumference of this nozzle, and that would be 0 as well. Uz is the velocity along the z direction. That's definitely not going to be 0, right? This is going to not be. Any question about the setup of that? So I'm not going to go through this derivation to get the Navier-Stokes equation in terms of radial or coordinates. This is pretty well established, pretty established method. You can find these in Wikipedia, pretty much any fluid mechanics textbook, etc. But there's going to be a few things that are going to cancel. Well, not a few. Pretty much everything here is going to cancel out. It's like just a few remaining terms. So I wanted to go through why some of these terms cancel out. First is actually was mentioned on Tuesday that we're talking about steady flow, and the change with respect to time of all these terms is going to be equal to 0. Right? Steady in terms of steady state. Right? So all the partials with respect to time. Okay, so running through these, in terms of everything that's going to cancel out, maybe a little. In terms of having to write this, and then this will be a line. So basically, this term is going to 0. We have, they're not even about canceling out all of them because some of them are going to go to 0 anyhow. But UR, we already said is equal to 0. Theta is equal to 0. Theta is equal to 0. The change in UR with respect to the coordinate, that's equal to 0. This is going to get one really quick. All these terms. Basically, every single term in the top two equations are going to go to 0. And when we get down to the end, we're trying to start from that in terms of Navier-Stokes. So this goes 0, this goes 0 for all the reasons given before. The change in z velocity with respect to z is going to be equal to 0. The reason for this, back to slides, we're saying that this is well developed. And a well developed means that we have some sort of velocity profile, and it's going to be interesting to take the argument it's a particularly long channel. So if we have a velocity profile at this location, this would be a velocity in the channel. It's going to be the same velocity profile. Okay, so it means that any edge effects in terms of what happens when you go from the wider reservoir to the nozzle, that essentially is out by the time we get to the region of the nozzle that we're consuming ourselves. You can think of this as an infinitely long nozzle. Okay, so this term, partial UC, which we can see, is equal to 0. Now we have the first non-zero term. Okay, so the partial of pressure with respect to. So back to our diagram again. Let me pull out these so you can see it a little better. All right, we're looking at this plug of material. We're saying on one side of the plug, the pressure is P. The other side of the plug is P plus delta P. Right, this one, Z direction. That means that the pressure must have changed as we went in the Z direction. Right. This is a non-zero term right here. We're ignoring gravity. Another non-zero term is the change in U or UZ with respect to R. Again, back to this diagram. Here's the velocity profile UZ. Okay. R direction, so the UZ is the velocity in this direction is a function of R. The velocity is the highest at the center of the channel, and we assume no slip boundary conditions, which is common for fluid mechanics, is 0 at the end. So the velocity definitely changes with the coordinates, that's the R coordinates. Does not change with theta, and because it's well developed, does not change with the. So we get this, I don't know how many Navier-Stokes equation, and all of a sudden it is down to 2 terms. With these assumptions. Any questions on why? Some of them do. So the fact that the partial with respect to time R is 0 would be effectively lambda. Partial also one that the partial with respect to say theta R would be. Yeah. All right, so we boil this all down and we get a single relationship. We have partial pressure. R partial UZ with respect to R. Okay. Any questions on that? So this has a solution to it. The solution is not too easy because we have a nonlinear. It's basically a nonlinear partial differential equation. So this is a fairly complex one to solve. But you can go to basically partial PDE tables and find a solution for this. The solution is R. Okay, and then from here we can start to apply boundary conditions. So boundary conditions. We have the no slip boundary condition. So this means that u z of uppercase R. This is no slip at the nozzle, right? So when the coordinate in the radial direction is uppercase R or fully at the wall, then UZ of R is equal to 0. Okay. And then we have that UZ of 0 is not equal to plus or minus. And we don't have infinite velocity at the denominator. Okay, so the fact that the velocity at the center is not equal to positive or negative infinity, if we say r is equal to 0, natural log of 0 is negative infinity, or the limit is negative infinity. So that means that C1 has to be that definition. We have UZ of R is equal to uppercase R is equal to 0. That means that 1 over 4 mu P PZ R squared plus C2 go to 0. That means that C2 negative 1 over 4 mu P PZ. Okay, any questions about that? Okay, so I'll bring this back together for UZ. Of R. Just adding up. So to draw what we're looking at here is, so we say one, we have an expression for the pressure drop per distance. Also, we have a function. So if we look at this function, we say that it's our constant pressure drop over our distance. We said that this function here is going to have this form. So dp dz, as we drew this up, dp dz is a negative number, right? Pressure is higher on the left, or d is small, than it is on the right. The pressure drop is dp dz is a negative number. We have r is equal to 0. That's right here. Velocity is at its maximum. So u z max is equal to 1 over 4 mu dp dz. Right, so this is where the velocity is at its max. If I go all the way out to the wall, being at r or negative r, velocity drops to 0, right? So the velocity profile in the cylindrical channel looks like this. you'll get better hand sketch. Right. So this tells us what is the velocity profile gradient. If you look back at the problem statement, we want to get what is the volumetric flow rate. So we already have pressure here. We don't have volumetric flow rate. What we can do is we can integrate this function over the entire nozzle, over the entire channel. So then what that means is this looks like some sort of surface like this. This is kind of my attempt at a three-dimensional version of the flow profile. Velocity highest in the center, small surface edge. I can then integrate the rings of this. Right? These are thickness dr. Calculus 2. This function, the value at that location, is uz of r. So if I want to know what is in some infinitesimal flow rate, dq, that's equal to the circumference at that location, that's 2 pi r. The actual value of the function there is v of r. And this says with dr. Try to look at units of this. R is in meters, right? uz is in meters per second, that's the velocity. And then dr would be meters as well. So this would give us units of meters cubed per second. So if I went on the flow rate, question here, and then plugging in my function for uz of r, which I already have. Bunch of constants. R to the little r to the third minus r uppercase r squared r and r. Where is this? No, it's looking at the diametric flow rate at some location along here. So here's my infinitesimal dr. Right, if I know the diametric flow rate at this location in the nozzle, I'm integrating from the center of the nozzle all the way up. Okay, then evaluating this integral here. Canceling out these are here. Okay, then evaluate this finally, I get that negative pi over dp dz r to the fourth over 8. Any questions about that? We're almost done. All right, last little piece of information. biostable piece of information we're looking at. The question is basically the write the well-known Huygens-Poisson equation. If I rewrite the prompt statement, it would make it clear that this channel is of length L. So I don't know if that was clear or not. The channel is of length L. And so if I look at this relationship, if I look at what is the change in pressure with respect to, change in pressure with respect to the z coordinate, we have a drop of delta p over distance L. Right? So dp dz is equal to delta p. So putting this all together here, gives us pi pressure r to the fourth over 8 mu L. The problem statement wanted it in terms of delta pressure with respect to Q. So that just means we're doing some algebraic calculation here. So we'll get to this a little bit more detail in a second, but the one thing to keep in mind here, look at this, is that this pressure drop for a given flow rate is linearly dependent on the length of the channel. In terms of, we get into description of extrusion, the length of the nozzle is going to matter a little bit. What's really going to matter is the radius of that nozzle, right? Because we have a R to the fourth power. That can make a huge difference. This So this is your standard velocity distribution in a channel. This is kind of what I drew by hand very crudely, just so you can see a little bit better. Again, velocity is the highest in the center. Okay. Next thing I want to show here is that we have this relationship. I'll just redraw. I'll just rewrite it on this plastic carbon. We have a delta P is equal to L so those of you who have taken fluid mechanics system now, who has seen circuit analogy to fluid system? 2 people? Okay. All right. So this is we'll be leveraging this quite a bit for the rest of this module here. So I think it's important for I'll go through the 2 elements that will be important for a circuit analogy, and they're the resistor and the capacitor. So this nozzle here, so say for instance we have some sort of cylindrical channel, and I have a flow rate Q. Right? Because we're working with viscous fluids, we're always going to have a pressure drop. That's stated by this relationship, right? So viscosity goes up, pressure drop. This flow is going to be larger, right? So we're always going to have some sort of pressure drop. So we have fluid flow through this channel, and we have a drop in pressure as we go along this channel. So it's very common, especially in mechanical engineering systems, when we look at larger scale systems and systems integration, that we look at electrical circuit analogies of fluid circuits. And doesn't really change the problem. It just poses it in a way in which we can start to bring in tools from other fields to try to understand fluid. So because we have a fluid flow, and this is resistance, which leads to a pressure drop, pressure drop is always relative, right? It's always in reference to either gauge pressure or some pressure somewhere else. So what, in terms of electric circuit, what does that remind you? We usually think of things in terms of electrical circuits that we often call as potential, right? In terms of potential reference voltage. Right, so we don't, voltage is only is a relative measure, right? Saying something is 100 volts without saying what it's a reference to actually have a meaning. Same thing with pressure as well. So we have a analogy between a fluidic circuit, electrical circuit, as a pressure or voltage drop. So oftentimes, the electrical circuit, we say this is a change in voltage across the resistor. We have flow or conveyance of some sort of material. What is that? So in an electrical circuit, we often think of a current, so I running through this. And for this example, we're not going to get, we haven't gotten to the capacitances yet. We may do that. But we have, we write Ohm's law. Ohm's law is delta V is equal to I R. Right, so that's how we describe basically the relationships between the change in voltage going through resistance. So we have the same thing here. We have our analogies, right? Delta P is analogous to delta V. R, right? Where current is analogous to flow. So that means if we're looking at what is the equivalent resistance of one channel, yeah, so units on this. In electrical circuits, we always call ohms, right? But the other way to think about it is volts per amp, right? Here we're looking at pascals, seconds, meters, negative. It relates pressure in pascals to flow rate, which is a unit of meters cubed per second. Okay, so some basic relationships. This relationship, so resistance is linear, and viscosity and L. So if we double the viscosity, we double the resistance. If we double the length, we double the resistance, and vice versa. If we have any of these, and it's -4 power. And nozzle radius. So if I say I have two nozzles that I'm trying to print with, one has a radius of 1 millimeter, and I switch that to a 0.5 millimeter, I have basically multiplied my resistance by a factor of 2 to the 8th, by a factor of 16, right? To the 4th factor. Is that correct? Okay, thank you. Okay. All right. So the radius of this nozzle when we're doing material extrusion is very, very important. Of how much pressure we have to actually get flow to happen. You'll see the effects of this when we get into more of the systems analysis. I think it's important to look at this from a apply here. This is resistance. Again, three. And the main thing to point out here, this is a difficult scale to look at because this is 10 to the 11. But this is a very sharp transition here. Fairly low resistances, very high resistances. This is a zoom in, but still 10 to the 9. I just kind of give you a sense. That's actually 10 to the 9. That's all in this region. Okay, so there's a very, very, very sharp, distinct relationship between resistance and nozzle radius. And this is going to be very important when we start to understand what so we see that in the reservoir area, that the diameter is quite wide, or the radius is large, and the nozzle gets very, very small. So the dominant resistance in the system is coming all at the nozzle. And we'll get to this later in terms of why we're essentially ignoring resistance in this region, the reservoir region. But I think it's becoming pretty clear that the nozzle radius here is much more small in this area. So what actually affects the pressure drop in the system is all in the nozzle. Any questions on that? It's a good time to take, say, a 5-minute break. We get into, come back, we'll get into more complex fluids. And we can't run a resistance for this because it's not talking about or Newtonian fluids. We'll reconvene a little bit after. very similar problem to 7.1, except the only difference here is with 7.1 we're looking for Newtonian fluids, and this is looking at pseudoplastic. This is going back to module 3, where we first introduced the idea of what a pseudoplastic fluid is. But the main thing to point out is that pretty much every material that's used in material extrusion AM is a pseudoplastic or a yield pseudoplastic fluid, and that they are shear thinning fluids. So shear thinning fluids means, well, let me start with by contrasting what Newtonian fluid is. So Newtonian fluid is basically has this relationship that the shear rate, shear stress relationship is given by Q, right? So if this was a Newtonian fluid, we would write how shear stress is equal to mu times the shear rate, which is dc dr. Okay. And the Navier-Stokes equations are built on the assumption that you have. So as soon as we go into say, we have a pseudoplastic fluid, we can no longer use Navier-Stokes. Valid. But all is not lost. We can still solve this problem. But this pseudoplastic fluid has this relationship where it is the shear stress is nonlinear in the shear rate. Okay, so it's this exponent n. If it's shear thinning or pseudoplastic, that means n is less than 1. Go back to module 3. So pseudoplastic fluid would follow this curve right here, which means that the slope of this line is continually changing, and this means that the effective viscosity, which is the slope at any shear rate location, is the viscosity is going down as we shear this wall. Okay. So this is very common in polymers, alloys, anything you would extrude using material extrusion, and this is precisely because these random chains of either polymers or polymers in colloids, when it's under low shear, they tend to entangle, and then when you put them under shear, they align with each other, and therefore the viscosity goes down. Truth be told, that pretty much every material is truth be told, pretty much everything is a yield pseudoplastic fluid. I'm not going to go through this because it would take me an entire lecture to derive pressure and flow rate. So we'll stick with the simplification of this. The main difference between the pseudoplastic and yield pseudoplastic is that shear stress in yield pseudoplastic fluid I can erase. Let's break this somewhere else. Function of some sort of yield stress less than the pseudoplastic. So where this is the yield. Okay, so what this means is that you have to have a certain stress in the fluid before it'll start to move. The best analogy to a yield pseudoplastic fluid is toothpaste. Put on your brush, right? Maintain the shape. Doesn't look like it's solid. If you put it against your teeth, it starts to really like that. Okay. And there's a lot of materials that are yield pseudoplastic. That when there's no shear on them, they hold their shape, or hold some sort of three-dimensional. Okay. All right. So we have this this relationship here. If we look at this plug-in material, looking at the force balance, I have no idea. Okay, I'm going to tell you. If we look at the force balance on this this term here, if we look at what's going on the left-hand side, we understand it's a steady state. Plug is neither moving, but it's neither accelerating or decelerating. So if we look at our force balance, that's the sum of forces. Forces should equal 0 because we have MA is equal 0, acceleration is 0. So we have on the left-hand side, we have for this plug-in material, we're going to have P times pi r squared. Right? So we're saying this is cylinder here, and radius r, therefore it has area. On the left-hand side, resisting this is a pressure P plus delta P, again multiplied by pi r squared. P plus delta P on this side. Those are our pressure forces. We have also our shear stress forces. The shear stress all along the cylinder of this plug. The circumference of the plug is 2 pi r. The length of the plug is L, also schematic here. And then shear stress, tau r. This creates our force delta. So how we just all the forces act on this point. A lot of this is going to cancel out. For one, we have a P pi r squared minus P pi r squared. This term cancels out. One of these r's is going to cancel. This one r's. I don't know why. Let me just try. Really quickly try to get that. So when I wrote this out first, I missed the R here. That's what I was missing. All right, this cancels with this. Pi cancels here. All these R's cancel here. We get from the relationship that negative over PR is equal to 2 tau RZ. This is going to be the base equation that we're going to build everything. Also including this. So our equations for pseudoplastic fluid and this. So if I want to then solve for then the change in velocity UZ, we're plugging in this relationship into here, solving for unknown DUZ. The question is about. Okay. So now, ultimately, just like the previous one, we wanted to get an expression for the z velocity of the function, right? So we're trying to get the same point here. We want to get this equation here, just integrate both sides. Right side is switch to r, so I'm going to get a. Coefficient basically, so the exponent of r plus 1 and divide by that, right? We're integrating with respect to r. I'll show that in a second. So r now becomes always 1 over n. I integrate now becomes 1 over n plus 1. And of course divide the coefficient by that amount. Nothing happens in the delta p. Then we have, right? And then we can do a quick rearrangement here. There's some rearrangement. Say 1 over n plus 1 as equal to n plus 1 over n. Just make it quick. Then we get that negative n over 2 plus 1. So boundary conditions. U of R, uppercase R. Okay. So applying that to my equation to Z, I get that UZ uppercase R there. Basically, if I want to rewrite this, then I would just say that C then, basically I can move this whole thing to the left-hand side. C is equal to this one. So then my expression for U Z of R, so a few things that are in common with the previous expression. Before we had, let me just show this. Okay, so some things that are in common. Before we had delta P and did not raise any power, right? Here, so that'd be delta P to the 1, right? So here we have delta P to the 1 minus 1 over n power. And we said is less than 1. So this means that there's some sort of, the exponent of delta P is going to be greater than 1. That's one relationship to keep in mind here. So that the relationship between delta P and the actual velocity is somewhat amplified. Shear thinning, the higher the pressure, the faster it flows, lower the effective viscosity. These R terms, we saw these we were at this point as well. These are R squareds. Here there R to the n plus 1 over n. This is going to be very dependent on what n actually is in terms of what this value is, but they're just different. That's one thing. The next step that we took when we wanted to figure out what is the flow rate with respect to pressure is that we integrated this function UZ of R, took a little thin nullus of material, and we integrate it over the whole nozzle radius R. So we're going to do exactly the same thing here. So no change really from the previous solution. We're just filling in everything here. Then our term would have R uppercase N plus 1 over N times lowercase r. Then R N plus 1. So if I want to simplify this, N plus 1 over N plus 2 is equal to 3N plus 1 over N. Right? All right, 1 plus over denominator becomes 2N over N, right? Together? All right. So in terms of everything coming together here, this is just algebra to get to the next step. Then we're going to get that Q is going to be this. Simplifies fairly easily, nowhere near as simple as the Newtonian case. Again, we have an expression here. This expression is again, it relates to flow rate, right, of our material through a cylindrical channel with pressure. And also, we're going to see again a very strong dependence on R. Keep in mind that N is in the range of R1. Right? So we're going to get some sort of number, say for instance, B1 half, right? So we get 3 halves plus 1, right, which is equal to 5 halves divided by half. Actually, again, getting it part of 4. Some of the regions, we get a very strong influence on the channel radius on this relationship between flow rate and pressure. Still have a relationship between M, which you can think of as kind of the coefficient on this shear stress to shear rate relationship. This is somewhat equivalent to viscosity, not quite, as kind of a similar field to it. L has an influence. Everything still has an influence here. It's just slightly different because our fluid that we're looking at is proper shear stress. This is a very common pressure flow rate relationship in general extrusion. I think it's worthwhile to plot what this looks like for different materials. So if we were to say that this is a few extreme examples here, this N is equal to 0. So if we say if N is this relationship, shear stress is equal to N AZR, shear rate, and power. If we say that this is shear stress is always 0, then you just get a flat wall of material nozzle. Oh, sorry, just to help with taxes. This is the velocity in z direction. In this book, they call it uppercase V. In our book so far, we call this lowercase u. Right. So this is then the velocity in z direction as a function of r divided by the average velocity. So if this is n is equal to 0, then we get this flat wall. N is equal to 1, that's Newtonian fluids, right? That's what we just studied. That profile looks like. As n gets very, very large, these are what are called shear thickening materials. It's the opposite of shear thickening. This is coming from a book that talks about all types of non-Newtonian fluids. You essentially never see these in material extrusion because having a shear thickening material is just a really bad idea. It's tough to extrude something that gets thicker as you shear it, right? But shear thinning would be something we would definitely see. So where this was a purely parabolic profile before, this turns into something that has a different profile here. Have a flat region in the center, and then going out to the edges. So what it does is it changes the velocity profile. It also changes our pressure, flow rate relationship, things of that nature. Any questions on those basic questions? Okay. So the last 5 minutes, I guess what we talked about thus far is we talked about essentially flow in the nozzle region. Extrusion system, this is where R is this region we have R large. Okay, so resistance dominant in this region right here. Very small contribution in the reservoir region. And then we're going to talk about the idea of fluidic capacity. And that's going to be the actually opposite. It's going to be a volume dependent, so the volume material we're talking about. And to get into that discussion, I won't have to start 7.4, but I wanted to get into the idea of the bulk modulus. So the bulk modulus is essentially the ability of the material to store pressure. And it stores pressure by densification of some material. So other things that you may want to relate this to, bulk modulus is very similar to the Young's modulus of some sort of material. If you pressurize some material, there's a change in volume of that material. Since if you have a change in volume, you have a change in density. So if you take it from a cube, so isostatic pressure everywhere, the volume of this cube is going to get smaller. Right? Or the material is going to densify. And so what you've done, as long as it's reversible, what you've done is you've essentially stored pressure. So this relationship between the change in pressure and change in volume is given by what's called something called, or oftentimes given as variable beta. So you can relate it in terms of a change in pressure with a change in volume, or a change in pressure with a change in density. Okay. So basically, the idea that we have some sort of material that's under pressure, it will then store that pressure. Right. Going back to this, right? So we know that we have to have a pressure drop top of the nozzle to the bottom of the nozzle to get flow, and therefore extrude and build things with additive manufacturing. That means that we're going to have some sort of pressure in this reservoir, and we're going to actually be able to store energy in that reservoir. This is going to largely be seen as a detrimental effect. Okay, so by storing pressure, what it does is it requires you to have, say, these rollers move prior to when you actually want material to extrude. So you have to build up pressure first before this happens. And also, that would then pressure will continue to seep out even when you don't want material to be extruded, right? Because you have some sort of built up pressure that has to then release. So that's going to release through material going through the nozzle and depositing where you don't want it. We'll get into that certain machine designers that compensate for that effect. But this is a very real effect. Extrusion systems, the pressure storage, which is necessarily a bad thing. And pressure storage is required because they have to have a reasonably large pressure to extrude out of small nozzles. usually want small nozzles because we want small features. Any questions on that last thought before we adjourn until Thursday? Okay, see you on Thursday.